Hello everyone, in this video we will learn wind load calculation for pitch roofs of rectangular clad buildings. Now this is the 3D view of one industrial shed. Now some particular term we have to remember. Now this is the eave height, this height is the eave height, this is the ridge, these are the roof purlin, this gap is base spacing. Normally when we calculate the external pressure coefficient at that time, this particular length, that means the length on the longer side of the industrial set, that we will consider as L, and this particular length which is actually the shorter length, that we will consider as W. So longer length will be L, shorter length will be W, and H will be the eave height. Now we do not have to consider the height up to ridge. Eave height will be H, and this particular angle, that is the angle of the truss, will be the pitch angle or roof angle. The angle of the truss, that means how much the truss is inclined with horizontal, that will be the roof angle. All these data are actually required when we are calculating the external pressure coefficient for one pitched roof. Now, before we calculate the external pressure coefficient, first understand the flow line for different case, for different pitch angle. Like here you can see this is when the wind angle is 0 degree. 0 degree means wind will come and hit the longer side of a particular industrial shed. When wind will hit the longer side, it will be 0 degree wind angle, and when wind will come and hit the shorter side, that means W of the industrial shed, at that time we will consider that is 90 degree wind angle. Now this is when wind is coming from 0 degree, and here this particular point is actually the point of flow separation. Means here wind is separating out from the building. Here flow separation is not occurring. Wind is attaching with this particular building model up to this, and after that at the ridge point here actually wind is separating out from the building model. So this phenomena is very important, because when wind will separate out from the building model, just after the separation point, vortex will be formed. This vortex will be formed, and if we look for the velocity distribution, the red color is actually where wind velocity is high, and blue color is there where wind velocity will be low. So in this particular zone, here the wind velocity is quite high, and in this particular zone where vortex is formed, at that zone wind velocity is actually less. Here also wind velocity is very less. So one thing we have to remember always, that just after the separation point, for this separation point, when wind is detaching from the surface, there vortex will be formed, and when vortex will be formed, at that zone normally there will be negative pressure. Negative pressure means suction. In this zone, if there is vortex, then always there will be suction. Now here if you look for this figure also, in this particular point there is some flow separation, and in this point also there is some flow separation. So both this zone just after the flow separation point, this zone will be very much important, because just after the flow separation point, at that portion there will be some vacuum space, and due to this flow separation vortex will be formed, which will create huge amount of suction. So all that portion where there is vortex, at that zone there will be suction, but just after the flow separation point, at that point suction will be maximum. Here, but for this pitch angle 40 degree, here in this zone flow separation is not occurring. Wind is actually attached with this particular surface, but in this particular point, flow in the ridge point, flow is actually separating out from the surface. So this particular point is important, and after that this zone will be hugely affected by the wind suction. So this thing we have to remember. Now these are the streamlines when wind is coming from 0 degree. I have already mentioned that wind will be 0 degree when wind is coming and hitting the longer side of a particular industrial shed. Now these are the streamlines for different pitch angle, and here vortex is formed just behind the building model. This side we will say this side is windward side, and behind where vortex is formed, that side we will say that is leeward side. Now these are the clean images for wind pressure distribution diagram. These are the variation of external pressure coefficient for different case. Red means this for this particular zone it is positive pressure. Positive pressure means wind will push the particular phase. Wind will push this particular phase, it will be positive pressure. And if there is negative pressure means suction. Normally for roof, suction is mostly be there because in this zone there will be flow separation. In this particular line there will be flow separation, and wind will actually detach from the surface in this particular line, and flow separation is very important for this particular line. Just after the flow separation point, here you can see in this zone suction is there, in this zone suction is there, huge amount of suction is there. Now when pitch angle is 20 degree, here you can see that just after the separation point for this line also, for this line also, in this zone, for both this case, here you can see there is flow separation, and in this zone there is huge amount of suction. For both this zone there is huge amount of suction. But when the pitch angle is 40 degree, here you cannot see that much amount of suction, because here wind is directly hitting this particular phase, and here you will see normally positive pressure distribution. But after this line, after this ridge line, when wind will separate out from the particular model, at that time there will be some local suction after the ridge point. Now these are the flow lines when wind angle is 90 degree. This is when pitch angle is 0 degree, 20 degree and 40 degree. Now for all this case, flow lines are very similar. Behind the building model there is vortex formation, and in this particular point there is flow separation. So flow separation is occurring here, and as I have already mentioned that after the flow separation point there will be some suction. So that we have to remember for this case also. So if we see the 3D streamline, these are the streamlines around different building model. Again vortex is formed behind the building model and also on the side faces. Now these are the clean images, and you can see here that again just after the separation point in this zone there is huge amount of suction. Normally for all the model, if we look for this pitch roof, then also you will see normally there is suction, there is no positive pressure for the roof. But just after the separation point in this zone suction is maximum. So this zone will be very much affected for the local suction. So when we are doing the cladding design, at that time this particular zone where the flow separation is occurring, this zone will be very important. When we are doing the design of RC structure, at that time this type of flow separation and local pressure coefficient is not that much important, because at that time the sail point of building is quite high in comparison with the wind load. But when we are doing the design of a industrial shed, at that time the sail point of the industrial shed is not very high in comparison with the wind load. So this particular wind can actually cause damage to that particular portion. If we do not consider this local coefficient, and if we design all this pitch roof with particular one value of average pressure coefficient, then this in this particular zone there can be some failure. So in the local portion we have to design separately, in other portion we have to design separately, considering the average value. Now wind force can be calculated by using this equation. F equals to Cpe minus Cpi into A into Pd. Cp is the external pressure coefficient, and this is the most important term when we are calculating the wind pressure for pitch roof. At that time Cp is very important, and Cpi is the internal pressure coefficient. That we will also discuss that how to calculate the internal pressure coefficient. A is the tributary area of different member, and Pd is the design wind pressure. In a separate video I have already mentioned how to calculate the design wind pressure. Now that we will get from the I button, and that we will also get from the description. I have provided the link of this particular video by which you will get the understanding of how to calculate the value of design wind pressure. So design wind pressure we will know. We have to calculate the tributary area, and we have to calculate the external pressure coefficient and internal pressure coefficient to calculate wind force for a particular member of industrial shed. Now, this is the table of external pressure coefficient for pitched roof of rectangular clad buildings. Now here I have already mentioned that W is actually the shorter edge of a particular industrial shed building, and H is the eave height, not up to the ridge. H is the eave height. Now for calculating the external pressure coefficient, two parameters are required. One is the building height ratio and another is the roof angle. Roof angle is alpha and building height ratio is actually H by W ratio. So length is not important here. For different condition, length is not important. So we do not have to consider the length when we are considering the external pressure coefficient. Now for different case, we have to calculate the external pressure coefficient for different phases of the pitched roof. Now if I go for the next figure, then it will be easier to understand. Now suppose this is one building model and the dimension is like this. The length of the model is 40 meter, the width W is 25 meter and eave height is 15 meter. Roof angle is 20 degree. This is suppose one particular industrial shed model and we want to calculate the external pressure coefficient for this particular building model. Now for this building model, H by W ratio is 0.6. H is the eave height and W is the length of the shorter side. So H by W is 0.6 and alpha is 20 degree. So this is the value of external pressure coefficient from the previous table. Now when wind is coming from this direction, it will be 0 degree. And when wind will come from this direction, it will be 90 degree. Because if wind comes from this direction, it will hit the longer side which is 40 meter. When wind will come from this direction, it will be 90 degree. Now, when wind is coming from 0 degree, here you will see that the value of pressure coefficient for EF and GH is given. So, which one is EF? This is E, this is F, this is G, this is H. So, EF means this windward side. This windward side is actually EF, for which the external pressure coefficient is given, and GH is the opposite side. GH is the opposite side for which the pressure coefficient is also given. Here it is minus 0.7, here it is minus 0.5. And when wind is coming from 90 degree, then pressure coefficient is given for EG and FH. EG is this portion and FH is this portion. That means just after the separation point, that zone is EG. After the separation point, after some length, it will be FH. So both this zone is very important, but normally the suction is more for EG. Normally the suction is more for EG because flow separation is occurring in this particular position. After that, suction will be less. Now, these zones are also very important. Here you can see these zones are also very important. These are actually local suction zone. Local zone, we have to consider the local pressure coefficient, local coefficient for this particular zone. Now, this particular shaded area is actually, the value will be minus 1.5. So, this area means this area. Just after the separation zone for 90 degree. This area, for this area, we have to consider the local coefficient of minus 1.5. This particular zone we have to consider for 90 degree, but our code clearly not mentioned that this local coefficient we have to consider for which angle. For 0 degree and for 90 degree, for both this case, our code is specified that we have to consider local coefficient. So we will consider local coefficient for both wind angle actually, because our code is not clearly mentioned all this thing. Now this is for 90 degree, but we will consider the value of minus 1.5. Now this shaded area, this is this zone here. So this portion, just in this portion there will be the local coefficient of minus 1.5. After that, in this zone, here also in this zone, here also the local coefficient is minus 1.5. So here minus 1.5, here minus 1.5 and here also minus 1.5. and after the ridge line, after the, so two separation point, one is here, one is here. So after this point, that local pressure coefficient is minus 1.5, and after this separation point, here actually the value of local coefficient is minus 1. For our building, it is minus 1. So in this zone, it is minus 1. Now, how much is this length? This length in plan is given in our code. It is h or 0.15 w, whichever is smaller. So for our building, h is 15 meter and 0.15 w, 0.15 into w. So 1 minute. 0.15 into w is 3.75. 3.75. But this length is 3.75. But 3.75 is actually the length at plan, because this is the plan, key plan. So when we are considering the inclined portion, inclined pitch roof like this will be 3.75. Here in plan, this will be 3.75. So the inclined length, this length will be more. It will be 3.75 by cos alpha. Alpha is the roof angle. Cos alpha, because this is base, this is hypotenuse. So 3.75 by cos alpha, our alpha is 20 degree. So if we just calculate it, it is 3.99. 3.75 by cos 20 degree is 3.99. We can consider it 4. We can consider it as 4. So this local pressure coefficient we have to consider up to length 4 meter. Here we have to consider this length will be 4 meter. Here also it will be 4 meter. But we do not have to consider here actually, because for this particular local coefficient, the plan length and this length is actually same. So here actually it will be 3.75. But for these two case, it will be 4 meter and 4 meter, because in plan, if we consider the projection, then this projection it will be 3.75. But this length is 4. Here also, this is 4. Local coefficient, this is 4. The projection below is 3.75. And this length is 3.75 because its projection is also 3.75. So this is the zone of local coefficient we have to also consider. Now another thing is also important, that when wind is coming from 90 degree, we are saying Eg, this is Eg and this is FH. So how much is Eg and how much is FH, that our code has not clearly mentioned. It is mentioned that this is Eg, this is FH. But how much is Eg and how much is FH, that our code clearly not mentioned. And one thing is also there, that this particular table of CP actually independent of L. L may be any length. So code has not specified that how much will be this and how much will be this. Normally the suction is more for Eg. Always the suction will be more in this particular zone. So normally while doing the design, we will consider the suction value of Eg, not FH, because the value of Eg, the suction value of Eg will be always more than FH. So now if we go in this image, here you can see wind is coming from this direction. So this is 0 degree. And this is the front face. Here actually you can see in this zone, positive pressure is there. And in these two zone, there is, after the separation, in this zone there is huge amount of suction, local suction. So this value we will consider as minus 1.5. Minus 1.5, this value is for this zone. Here minus 1.5, and after the ridge line, here we will consider minus 1. From our table, we will consider this as minus 1. Minus 1.5 and minus 1. So if I go for a clear image, here, this is E, F, G and H. So the average pressure coefficient for this phase will be minus 0.7. The average pressure coefficient for this phase will be minus 0.5. Minus 0.5. And local pressure coefficient for this zone will be minus 1.5, and the local pressure coefficient for this zone will be minus 1. So this is when wind is coming from 0 degree. And when wind will come from 90 degree, then we have to consider this particular local coefficient. But our code has not specified that which local coefficient we have to consider for which wind angle. For 0 degree or 90 degree, we have to consider this. Our code has not specified it. So we have to consider this local coefficient for all wind angle actually, for 0 degree also, for 90 degree also. So we have to consider all local coefficient. Here also, the local coefficient is minus 1.5. Now this length is 4 meter. Inclined length is 4 meter. The projection is 3.75. Sorry, 4 meter. And this length is 3.75 meter. This length is 3.75 meter because its projection is also 3.75 meter here. Now this is when wind is coming from 90 degree and hitting the shorter edge. Shorter edge when it is hitting at that time, this will be the pressure distribution and this is the zone of local coefficient. This is the zone of local coefficient. In the side face also you can see that after the separation point, here also wind will separate and vortex will be formed like this. In this zone also there is some local suction. But now we are considering the roof portion, so we will consider this zone actually. So here we have to also consider the local suction. Now this face is EF and this is GH. For 90 degree wind angle, we will consider EG and FH. So this is the zone of EG. Here this is the EG. Here the local suction is minus 0.8. Sorry, here the average suction is minus 0.8, not the local. And for FH, the local suction is minus 0.6. And we are saying that we will consider the value of EG for throughout the route, because our code has not specifically mentioned that this much portion is EG, this much is FH. So we do not know the length, so we will consider the value of EG throughout the route. And one thing is also important, now we are considering this is 90 degree. We can also consider this for 90 degree also. We can consider from this side also, we can consider from this side also. At that time it will be EG and after that there will be FH. So there is no need to calculate separate EG for this portion or this portion. So it is better if we be on a safer side. It is better if we consider the external pressure coefficient of EG for throughout the route for both sides. Here also if we consider the value of EG and in this side also if we consider the value of EG, then we will be on the safer side. So we will consider the value of minus 0.8 for total route. In this zone actually minus 0.8, in this zone actually minus 0.8. After that it will be minus 0.6, but we will consider minus 0.8 throughout the route because our code has not specified that up to how much it will be EG, up to how much there will be FH. That our code has not specified, so we will consider this particular value. 0.8, minus 0.8. And we have to also consider the local suction zone. So here for 90 degree, this is the local suction zone. This zone is local suction zone. So we will consider this zone for local suction. But our code has not specified that which local coefficient we have to consider for which angle. So we will consider for all portion actually. Here also we will consider local suction. Here also we will consider local suction. Now we have considered 0 degree this particular direction. If wind is coming from this direction, 180 degree, at that time here there will be local suction in this zone and here there will be local suction in this zone. So that we have to consider that which particular wind direction is our wind direction. Based on that we have to design. So now after calculation of external pressure coefficient, we have to calculate the internal pressure coefficient. And internal pressure coefficient is totally dependent on the opening area of building. If the opening area, this is the opening area, that how much percent is the opening area. So if the opening area is less than 5%, less than equals to 5%, then we have to consider internal pressure coefficient of plus minus 0.2. If the opening area is in between 5 to 20%, we have to consider the internal pressure coefficient as plus minus 0.5. And if the opening area is greater than 20%, we have to consider the internal pressure coefficient as plus minus 0.7. So what is plus and what is minus? Plus means pushing of a particular phase. If wind is pushing a particular phase, pressure, positive pressure, at that time we have to consider the value plus 0.2. When wind is pulling a particular phase, at that time we have to consider the minus value. So if plus 0.2, then it will push the particular phase, and if it is minus, it will pull the particular phase. And both can actually occur inside a building. Based on the wind direction and wind property, there can be pressure, there can be suction. So we have to consider both these two case of internal pressure coefficient for doing the analysis, proper analysis of our pitch roof. Now suppose we are considering wind angle 0 degree and CPI plus 0.5. Wind angle 0 degree and CPI plus 0.5. Wind angle 0 degree means this is our building, and wind is coming from this direction and hitting the longer side. So this is EF, and the opposite side will be GH. This will be GH. So for EF, the external pressure coefficient is minus 0.7, and for GH, the external pressure coefficient will be minus 0.5. So minus 0.7 and minus 0.5. Now if the internal pressure coefficient is plus 0.5, and this is the local coefficient, here minus 1.5 and here minus 1. So in this zone of 4 meter, and in this zone of 4 meter, in projection it will be 3.75. It will be 3.75. The lesser value of H and 0.15 W. The lesser value, that is 3.75, and here it is 4 meter. So in this zone we have to consider local coefficient, here minus 1.5, here minus 1. And for this particular condition, CPI is plus 0.5. CPI plus 0.5 means it is pushing this particular phase. CPI positive means push, negative means pull. So now we have to calculate the CP minus CPI. For this phase, minus 0.7 minus 0.5, so minus 1.2. Minus 1.5 minus 0.5, it will be minus 2, minus 2. Minus 1 minus 0.5, it will be minus 1.5. And minus 0.5 minus 0.5, it is minus 1. So actually all these are suction. External pressure coefficient is suction, which is acting outward. And the internal pressure is also pushing the pitch roof. So actually both are acting on same direction. It is also outward, it is also outward. So both are actually, one will actually increase the value of other. So when we will calculate CP minus CPI, the value will be obviously more, and this value you have to consider while doing the design. This is up to 4 meter, this will be rest. And this minus 1.5 up to 4 meter, and this will be rest. Now this is when CPI is minus 0.5. CPI is minus 0.5. So this is the value of CP for EF and GH, minus 0.7, minus 0.5. And this is the local coefficient, same like the previous problem. Now CPI is minus 0.5. CPI is minus 0.5. Minus means it will pull the phase. Minus 0.5 means it will pull the phase. So here actually you will see that one is balancing the other. One is balancing other, so value will decrease. Now here the CP minus CPI, if we calculate CP minus CPI for this case, it will be minus 0.7 minus minus 0.5. So it will be minus 0.2. So minus 0.2. Here minus 1.5 minus minus 0.5. So it will be minus 1. Here minus 1. Minus 1 minus minus 0.5. So it will be minus 0.5. Here minus 0.5. And here minus 0.5 minus minus 0.5. So it will be 0. 0. So here 0. So up to 4 meter minus 1. After that it will be minus 0.2. Here minus 0.5. And rest will be 0. Here in this portion we do not have to consider any pressure coefficient if CPI is minus 0.5 and wind angle alpha equals to, wind angle is, alpha is the pitch angle, wind angle is 0 degree. At that time in this zone we do not have to consider any external pressure coefficient, any CP minus CPI. So now this is the case of when the wind angle is 90 degree and CPI is plus 0.5. Now here we have to consider the value of EG and FH. Now I have already mentioned that wind is coming from this direction, it will be 90 degree. This will be EG and this portion will be FH. So EG is the first portion and FH will be the afterward portion. but our code has not mentioned that how much is EG and how much is FH. So we will consider the value of EG for total roof. Total pitch, we will consider the value of EG because the value of EG is actually more. Minus 0.8 is actually more suction than FH. So we have to consider minus 0.8 here. We have to also consider minus 0.8 here. Throughout the roof, we will consider minus 0.8 for both this side. So minus 0.8 and local suction is here minus 1.5 and minus 1. This minus 1.5 is applicable for this zone. For this zone, actually, if I clearly draw it, this minus 1.5 is applicable for this zone. But if we clearly think about a purlin, then for one purlin, only some particular zone will be affected by this particular local coefficient. But this particular local coefficient is very important, or this local coefficient is very important. Because the local coefficient on the other side, that means this local coefficient is very important, because it may happen that one purlin is coming inside the effect of the local suction. So this purlin can be affected by the local coefficient. So this particular direction is more important of local coefficient than this direction. This local coefficient is not that much important. These local coefficients are more important, because some particular purlin can be thoroughly affected by this local coefficient. If the purlin is placed near the edge, in this portion if there is one purlin, or in this portion if there is one purlin, or in this portion or in this portion, then that throughout the purlin will be affected by the local coefficient. So this local coefficient we have to consider here minus 1, here minus 1.5, and for both EG and FH, the average value is minus 0.8 we have to consider, because we will consider the value of EG throughout the roof. So this is the CPE. Then if we consider CPI for plus 0.5, then CP minus CPI will be like this. CP minus CPI will be like this, because here minus 1.5 minus 0.5 will be minus 2, minus 0.8 minus 0.5 will be minus 1.3, minus 1 minus 0.5 will be minus 1.5, and minus 0.8 minus 0.5 will be minus 1.3. So this will be the image of CP minus CPI, CP minus CPI. And up to 4 meter we will consider minus 2. After that we will consider minus 1.3. Here up to 4 meter minus 1.5. And after that we will consider minus 1.3. So now this is when wind angle is 90 degree and CPI is minus 0.5. Here this is for EG portion and this is for FH portion. And these are the local coefficients. Minus 1.5 and minus 1. And this is CPI. CPI is minus 0.5. CPI minus 0.5 means it is acting inward. CPI minus 0.5 means it is acting inward. So CPI is actually here balancing the CPE. CPE is acting outward and CPI is acting inward. So both are balancing each other. So CP minus CPI will be like this. Here it will be minus 1.5 minus 0.5. So minus 1. Minus 0.8 minus 0.5. So minus 0.3. Minus 1 minus 0.5. So it will be minus 0.5. And here minus 0.8 minus 0.5. So it will be minus 0.3. So this is the value. And this is the value of CP minus CPI. CP minus CPI. This local value we have to consider up to 4 meter. Rest we have to consider minus 0.3. Here local value we have to consider minus 0.5. After that we have to consider minus 0.3. Now this is one industrial shed. Now suppose we are calculating the value of wind force. Because now we know the value of CP minus CPI. CP minus CPI, we have calculated CP minus CPI for 4 different cases. One case when wind angle is 0 degree, CPI is plus 0.5. Because for our case, the opening area is in between 5 to 20%, 5% to 20%. So CPI is plus 0.5. Now another case is wind angle is 0 degree, CPI is minus 0.5. Another case is wind angle 90 degree, CPI plus 0.5. Another case is wind angle 90 degree, CPI minus 0.5. So these 4 are different cases. And for all these cases, we have calculated the value of CPE minus CPI. We have calculated the value of Cp minus Cpi for all this case. For different zone, we have calculated the value of Cp minus Cpi. And suppose wind is coming from 0 degree. 0 degree means this can be 0 degree. 0 degree means wind is hitting the longer side of a particular building. Now, suppose we are considering this purlin, this particular purlin. At that time, this purlin will be affected by the local coefficient. So, when we will consider the Cp minus Cpi, this phase will be the phase EF and the opposite side it will be GH. So, this phase is EF. We have to consider the Cp minus Cpi value of EF for this particular phase because wind is coming from this direction. This is 0 degree. And in this zone, up to 4 meter, we have to consider the local coefficient. In this zone, we have to consider the local coefficient. If there is some purlin in this zone, that purlin will be affected by the local coefficient. And after that, we will consider the normal value, normal Cp minus Cpi value. So, Cp minus Cpi you already know. Previously, I have discussed that. What is the value of Cp minus Cpi? Now, wind force is actually Cp minus Cpi into area into PD. Area is actually the tributary area. And at that time, if we multiply by tributary area, we will get the total force. How much force is coming, that we will calculate, that we will get. But when we are, if we are suppose designing one purlin, now when we will design purlin, at that time area is not very important. Because for purlin, suppose there is one purlin like this, there is one purlin. Normally for purlin, we will consider the UDL, that how much UDL is coming over this particular purlin due to wind. Normally wind will be in outward direction because it will be suction. So wind will come like this, it will be suction, but it will be UDL. It will be thoroughly distributed throughout the length. It is not concentrated in a particular point. So when we are designing a purlin, we will consider in place of A, we will consider Cp minus Cpi into influence width into PD. PD you already know, PD from previous video you will know how to calculate PD. Now how much will be the influence width of purlin? The influence width of purlin will be half in this side and half in this side. That means for this purlin, if we consider this purlin, this is connected with this zone and this zone. Now half portion load, here half side load will come in this particular purlin and half side load will come in this particular purlin. Now where the rest load will go, this half load will go in the next purlin. So if we think for this purlin, the influence length will be and influence width will be this. This will be the influence width. The total wind load of this total area will come over this particular purlin. Similarly, if we consider this portion here, this is the influence width of this purlin. So for any purlin, if suppose these are two purlin, these are three purlin connected. Now half from this side and half from this side, this much load, this load will come over this particular purlin. And the next part, this part, here the load will go for next purlin. So for this purlin, the influence width will be this. And when we are considering the UDL value, because for purlin we will calculate the UDL value of wind load, wind pressure, at that time we will consider the influence width. Because the load is applied throughout the length. Throughout the length, the UDL will be applied. So we have to multiply by just width. So multiply by width. So in this way, we will get the value of the wind UDL over a particular purlin. Now apart from that, suppose we are analyzing one truss element, like this truss element. So for truss element also, if we are analyzing, then we have to know the wind, different wind force coming over a particular truss element. That we have to also know when we are doing the calculation of wind load over a particular truss element. Now that load is, this load is actually nodal load. This is not the UDL value of purlin. This is the nodal load. So suppose we are considering this truss element. Then for this node, how much load will come? This is the same concept of tributary area that we have to consider. Like for this node, half in this side and half in this side, and half in left and half in right. So this total area will come under the influence of this particular node. That means the total load, wind load coming over this particular zone we will consider that total this wind load will actually come over this particular node. So that load can be this. Now for this node, suppose we are considering this node. So half in left, half in right, half in left, half in right, half in top and half in bottom. So this total area will come under the influence of this particular node. If we consider this node, half in left, half in right, like this. If we consider this node, it will look like this. This will be its influence length, because in this side there is nothing. So half in this side and half in top and half in bottom. So this will come under the influence of this particular node. For this node, it will be here. It will be a small influence area. This will be the influence area for this node. So in that way, we can calculate the wind force for different nodal position. And after we get the nodal position by using this equation, F equals to Cp minus Cpi into area into Pt. Area into Pt. So if we know the Cp minus Cpi for different position, I have already discussed that how to calculate the Cp minus Cpi for different position of a particular pitch group. Then after we get the Cp minus Cpi value, then we know the influence area. I have already mentioned that how to calculate the influence area when we are calculating the nodal load. When we are calculating the wind UDL for purlin, at that time we will consider nodal width, the tributary width for purlin. Here we will consider the influence area, and PD will be the design wind pressure. And how to calculate the design wind pressure, that I have already mentioned in one previous video. The link of that previous video you will get in the description, and I have also added that in the I button above. So check that video as well. I have also prepared another video for calculating wind force for a rectangular building, not the pitch roof, normal rectangular building we have calculated wind force. That video you can also check. So thank you for your attention. Have a nice day.